The morning of March 7, 1944, at Wright Field in Dayton, Ohio, a Packard Merlin engine mounted on a test stand had been running continuously for 6 hours. The engine powered a P-51 Mustang propeller spinning at 2,670 revolutions per minute. Engineers from North American Aviation and the Army Air Forces stood in the observation room, watching temperature gauges and listening to the mechanical symphony of pistons, valves, and a single critical component that should have failed 2 hours ago. The component was a roller bearing. Specifically, it was a deep groove ball bearing manufactured by the SKF company, redesigned with tolerances measured in 10,000ths of an inch, sitting inside the propeller reduction gearbox. According to every engineering manual, every calculation, and every previous test, this bearing should have overheated and seized. The gearbox oil temperature had climbed to 240 degrees Fahrenheit. The bearing was spinning at speeds that generated friction loads beyond its rated capacity. Yet the engine continued running smoothly. One engineer, a man named Harold Youngren from Packard Motor Car Company, checked his stopwatch again. 6 hours, 14 minutes. The P-51 had never flown a combat mission longer than 4.5 hours. The limiting factor wasn't fuel. It wasn't pilot endurance. It was this bearing. If it failed at altitude over enemy territory, the propeller would seize, the engine would tear itself apart, and the pilot would have perhaps 90 seconds to bail out before the aircraft became unflyable. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Youngren had spent 8 months redesigning this single component. He had argued with metallurgists, fought with procurement officers, and violated at least 3 Army specifications to make it work. His superiors at Packard had told him it was impossible. The bearing manufacturers had told him the tolerances couldn't be achieved in mass production. The Army had told him they didn't have time for experimental designs when they needed fighters in the air over Germany right now. But Youngren had seen the combat reports from the 8th Air Force. He had read the intelligence summaries describing how German fighters would wait just beyond the range of American Escort fighters, then attack the bomber formations with impunity. He had attended the briefings where they calculated that for every month the P-51's range remained limited, another 200 American bombers and 2,000 American aircrew were lost over Europe. The war in Europe in early 1944 was being decided by a mathematics problem disguised as an engineering challenge. American B-17 and B-24 bombers could reach Berlin, but their fighter escorts could not. The Republic P-47 Thunderbolt, despite carrying external fuel tanks, could escort bombers only as far as the German border before turning back. The Luftwaffe knew this. They positioned their fighter groups inland, beyond escort range, and attacked the bomber formations methodically. The losses were unsustainable. The P-51 Mustang had the aerodynamics to fly farther. It had the fuel capacity with external drop tanks to potentially reach Berlin and return. What it didn't have was an engine and propeller system that could run reliably for 8 continuous hours at combat power settings. The weak point, the single component that limited everything else, was a bearing that measured 3.5 inches in diameter and weighed less than 2 pounds. At 6 hours and 30 minutes, Youngren ordered the test continued. The other engineers exchanged glances. They had already exceeded the test protocol by 2 hours. But Youngren wanted to know exactly where the failure point was. He needed to understand how much margin they had, how much safety factor existed between normal operation and catastrophic failure. The engine continued running. The bearing continued spinning. And somewhere over Germany, bomber crews were climbing into their aircraft, preparing for another mission without adequate fighter protection. To understand why a single bearing mattered so much, you have to understand what the 8th Air Force was attempting to do in 1944, and why it was considered nearly impossible. The strategic bombing campaign against Germany was predicated on a doctrine developed in the 1930s by American air power theorists. They believed that heavily armed bombers, flying in tight defensive formations, could fight their way to targets deep in enemy territory without fighter escort. The bombers' combined defensive firepower would protect them from enemy fighters. Precision bombing would destroy Germany's industrial capacity. The war could be won from the air. This doctrine was tested in combat beginning in 1942, and it failed catastrophically. German fighters developed tactics specifically designed to defeat bomber formations. They attacked from head-on, where the bombers' defensive guns had limited fields of fire. They used rockets and heavy cannons that could engage from beyond the range of the bombers' 50 caliber machine guns. They concentrated their attacks on single bombers, overwhelming the defensive fire and destroying aircraft one at a time until the formation's defensive capability collapsed. The numbers told the story with brutal clarity. On October 14, 1943, the 8th Air Force sent 291 B-17s to attack ball-bearing factories in Schweinfurt, Germany. 60 bombers were shot down. Another 17 were damaged beyond repair. 600 airmen were killed or captured. The mission reached its target and dropped its bombs, but the losses were so severe that deep penetration raids into Germany were temporarily suspended. The 8th Air Force simply could not sustain casualty rates of 20% per mission. Fighter Escort was the obvious solution, but range limitations made it impractical with existing aircraft. The P-47 Thunderbolt, the primary escort fighter in 1943, had an internal fuel capacity of 305 gallons. With external drop tanks adding another 200 gallons, the P-47 could escort bombers approximately 475 miles from its base in England. This covered the Ruhr industrial region and parts of northwestern Germany, but it left Berlin, Munich, and most of Germany's critical industrial areas beyond escort range. The P-38 Lightning had better range, capable of escorting bombers about 520 miles with drop tanks. But the P-38 suffered severe problems at high altitude and the cold temperatures over northern Europe. Engines failed, turbochargers malfunctioned, and pilots developed frostbite in the cockpits. The P-38 groups experienced higher mechanical failure rates than combat loss rates. The P-51 Mustang entered service with the 8th Air Force in December 1943, equipped with the Packard-built version of the British Rolls-Royce Merlin engine. The aircraft immediately demonstrated superior performance. It was faster than the P-47, more maneuverable than the P-38, and critically, it was more fuel efficient. The Merlin engine consumed approximately 70 gallons of fuel per hour at cruise settings, compared to 90 gallons per hour for the P-47's radial engine. With internal fuel tanks holding 184 gallons, plus two 75-gallon drop tanks, the P-51B could theoretically escort bombers 650 miles from base. This was better, but still insufficient. Berlin was approximately 570 miles from the American bases in England. A round trip required 1,140 miles of range, plus reserves for combat maneuvering and unexpected weather diversions. The P-51 needed at least 1,300 miles of total range to reliably escort bombers to Berlin and back. North American Aviation, the manufacturer, added an 85-gallon fuselage fuel tank behind the pilot's seat in the P-51B and subsequent D models. This increased internal fuel capacity to 269 gallons. Combined with external tanks, the P-51 now had enough fuel capacity for the mission. On paper, the range problem was solved. But fuel capacity meant nothing if the engine couldn't run reliably for the entire mission duration. A flight to Berlin and back required approximately 7 to 8 hours of continuous operation, including combat time over the target area. The Packard Merlin engine had been designed for the shorter duration missions typical of air defense operations over Britain. Nobody had tested whether the engine's components, particularly the high-stress elements in the propeller reduction gearbox, could survive 8 hours of continuous operation at the temperatures and vibration levels experienced in combat. The propeller reduction gearbox on the Packard Merlin V1650 engine was a precision mechanical assembly that translated the engine's crankshaft rotation into propeller rotation at the optimal speed. The engine produced maximum power at 3,000 revolutions per minute. The propeller achieved maximum efficiency at approximately 1,600 revolutions per minute. The gearbox reduced the rotational speed while increasing torque, using a planetary gear system with multiple reduction stages. Every gear in this system rode on bearings. These bearings had to support radial loads from the gear teeth, thrust loads from propeller forces, and maintain precise alignment under temperatures ranging from 40 degrees below 0 Fahrenheit at altitude to 250 degrees Fahrenheit in the gearbox during maximum power operation. The bearings had to function in an oil bath, maintaining their lubrication film under extreme pressure while allowing oil to flow through for cooling. The critical bearing, the one that Harold Youngren had redesigned, sat at the output shaft of the reduction gearbox, directly behind the propeller hub. This bearing experienced the highest combination of speed, load, and temperature in the entire power plant. It was a deep groove ball bearing, type 6308, with an outer diameter of 3.5 inches and an inner diameter of 1 5/8 inches. It contained 9 hardened steel balls, each measuring 7/16 of an inch in diameter, running in precision ground raceways. Standard bearing design practice in 1943 specified radial clearances of approximately 3 to 5/1000ths of an inch between the balls and the raceways. This clearance allowed for thermal expansion, manufacturing tolerances, and wear during operation. It also allowed a thin film of lubricating oil to maintain separation between the rolling elements and the raceways, preventing metal-to-metal contact that would cause rapid wear and failure. Youngren's analysis of bearing failures in extended duration tests revealed a problem that seemed unsolvable. As the bearing temperature increased beyond 200 degrees Fahrenheit, the oil viscosity decreased significantly. At 240 degrees, the oil film thickness dropped below the critical minimum needed to prevent contact between the balls and raceways. Once metal-to-metal contact occurred, even microscopically, friction increased exponentially. The bearing temperature rose further, the oil broke down completely, and catastrophic failure followed within minutes. The conventional engineering solution was to increase oil flow through the bearing, carrying away more heat and maintaining oil film thickness. But the gearbox oil system was already operating at its maximum flow rate. Increasing flow required larger oil pumps, larger oil coolers, and modifications to the entire engine lubrication system. These changes would add weight, reduce reliability, and require 18 months of testing and certification. The 8th Air Force needed extended-range P-51s in 6 months, not 18. Youngren proposed a solution that violated standard bearing design principles. He specified reducing the radial clearance to 1.5/1000ths of an inch, less than half the standard clearance. This tighter clearance would maintain better oil film thickness at high temperatures. The reduced clearance would also limit how much the bearing components could deflect under load, reducing internal friction and heat generation. Every bearing engineer he consulted told him this wouldn't work. Tighter clearances meant the bearing would be more sensitive to thermal expansion. If the shaft expanded slightly more than the bearing housing during operation, the clearance could disappear entirely, causing the bearing to seize. Manufacturing bearings to tolerances of 1.5/1000ths of an inch would require significantly better quality control. Any contamination in the oil, any slight misalignment during installation, any manufacturing defect would cause immediate failure. The SKF Bearing Company, the primary supplier, initially refused to manufacture bearings to Youngren's specifications. Their production manager explained that their current grinding and honing processes could hold tolerances of 0.003 reliably, but achieving 1.5/1000ths would require retooling their manufacturing equipment and implementing statistical process control methods they didn't have. The rejection rate would be high. The cost per bearing would triple. Youngren went to the Army Air Force's procurement office with combat loss data. He presented calculations showing that if P-51s could escort bombers to Berlin reliably, the bombing campaign would become sustainable. The loss rate per mission would drop from 15% to perhaps 4%. This would save approximately 300 bombers per month and 3,000 aircrew. He argued that the Army should pay whatever the bearings cost and accept whatever delivery delays were necessary to get them right. The procurement officers were skeptical. They had heard promises about miracle components before. They wanted proof, not calculations. They authorized a limited production run of 200 bearings manufactured to Youngren's specifications, to be used in controlled testing. If the bearings survived 100 hours of testing without failure, they would consider broader implementation. SKF assigned their best machinists to the project. They modified grinding wheels, adjusted coolant flows, and measured every bearing with precision instruments. The first batch of bearings showed promise in initial tests, but 3 failed prematurely during thermal cycling tests. The grinding process was leaving microscopic stress risers in the raceways. SKF changed their grinding procedure, adding a stress relief heat treatment step after final grinding. The second batch of bearings performed better. Youngren installed them in a Packard Merlin engine at Wright Field and began the extended duration test that was still running on that morning in March 1944. He had already completed dozens of shorter tests, gradually increasing duration and severity. This test was designed to prove the bearing could survive a full Berlin mission profile, including maximum power takeoff, extended cruise at combat settings, and simulated air combat maneuvering that would increase loads and temperatures. At 6 hours and 45 minutes, one of the younger engineers asked Youngren if they should shut down the test. They had exceeded any previous endurance run by more than 2 hours. They had proven the concept. Running the test longer only risked a failure that would undermine confidence in the design. Youngren shook his head. He wanted to see the margin. He wanted to know how far beyond the minimum requirement the bearing could survive. Because in combat, nothing ever went according to plan. Pilots would push engines harder than design limits. Combat damage would affect oil systems. Maintenance crews working in freezing conditions would make installation errors. The bearing needed to survive not just the perfect mission profile, but the messy reality of aerial warfare. At 7 hours, the test engine was operating in conditions no Packard Merlin had experienced before. The gearbox oil temperature had stabilized at 238 degrees Fahrenheit, just below the threshold where conventional bearings typically failed. The bearing Youngren had redesigned was spinning at 2,670 revolutions per minute, supporting a radial load of approximately 800 pounds from the propeller shaft while simultaneously handling thrust loads that varied with each propeller blade passage. The physics of what was happening inside that bearing were extraordinarily complex. Each of the 9 steel balls was rolling through the raceways, completing approximately 445 revolutions per minute relative to the bearing's stationary outer race. At every point of contact between ball and raceway, pressures reached 90,000 pounds per square inch. The oil film separating these surfaces was approximately 50 millionths of an inch thick, thinner than a human hair by a factor of 2,000. This oil film was everything. If it broke down, even locally, even for a fraction of a second, metal-to-metal contact would occur. At these pressures and speeds, metal-to-metal contact would generate temperatures exceeding 1,000 degrees Fahrenheit at the contact point. The bearing steel would undergo phase transformation, losing its hardness. Wear would accelerate catastrophically. Within minutes, the bearing would seize. Youngren's reduced clearance specification was maintaining that oil film by controlling how the bearing components deflected under load. In a conventional bearing with 5,000ths clearance, the balls could shift positions slightly under load, creating variations in the oil film thickness. These variations meant some contact points had thicker films and some had dangerously thin films. The thin spots were where failures initiated. With 1,500ths clearance, the balls couldn't shift as much. The oil film thickness remained more uniform across all contact points. The reduced clearance also meant the contact area between ball and raceway was slightly larger, reducing the peak contact pressure. Lower pressure meant lower friction, which meant less heat generation, which meant the oil maintained its viscosity better. But achieving this required manufacturing precision that pushed the limits of 1940s production technology. The raceways had to be ground to within 5/10,000ths of an inch of their nominal diameter. The balls had to be within 2/10,000ths. The surface finish had to be smooth to within 8 millionths of an inch, measured with precision profilometers that few factories possessed. SKF's manufacturing process for these bearings required 14 separate operations. The bearing rings started as forged steel blanks, heat-treated to achieve Rockwell hardness of 60 to 62 on the C scale. They were rough machined, then finish ground on specialized machines that held tolerances within 10,000ths. After grinding, the rings were subjected to magnetic particle inspection to detect any microscopic cracks or inclusions in the steel. The balls were manufactured separately, starting as sphere blanks that were progressively ground and lapped to achieve perfect sphericity within 2/10,000ths of an inch. Each ball was individually measured with precision micrometers. Balls that measured outside the tolerance range were rejected, even though they might be perfectly acceptable for standard bearing applications. Assembly required clean room conditions, though that term wasn't used in 1944. The assembly room at SKF's Philadelphia plant was maintained at positive air pressure with filtered air to minimize dust contamination. Workers wore lint-free garments and assembled bearings on workbenches covered with clean white paper that was replaced between each bearing. Any visible particle of dirt, any fingerprint on the bearing surfaces, would cause the bearing to be disassembled, cleaned, inspected, and reassembled. The quality control inspection process was equally rigorous. Each completed bearing was measured for radial clearance using precision go-no-go gauges. The bearing was then mounted on a test spindle and rotated at low speed while inspectors listened for any unusual sounds that might indicate a defect. Bearings that passed visual and auditory inspection were subjected to a thermal cycling test, heated to 250 degrees and cooled to -40 degrees 3 times, then remeasured to verify the clearances hadn't changed. Out of the first production batch of 200 bearings manufactured to Youngren's specifications, SKF delivered 143 bearings that passed all inspections. 57 were rejected for various defects, 14 for incorrect clearances, 23 for surface finish defects, 12 for dimensional errors in the raceways, and 8 for suspected material defects. A rejection rate of 28.5% was extraordinarily high by normal bearing manufacturing standards, where rejection rates of 5% were typical. But Youngren argued that a 28% rejection rate was acceptable if the bearings that passed inspection were genuinely capable of 8-hour operation. The cost per acceptable bearing was approximately $18, compared to $6 for standard bearings. For a single P-51 engine, which required 12 critical bearings in the reduction gearbox and accessory drives, the additional cost was $144 per engine. The Army Air Force's procurement office initially balked at this cost increase. $144 per engine, multiplied by the planned production of 5,000 P-51s in 1944, meant an additional $720,000 just for bearings. They questioned whether this expense was justified for a theoretical improvement that hadn't been proven in combat. Youngren responded with a different calculation. If extended-range P-51 escorts reduced bomber losses from 15% per mission to 4%, each mission that previously lost 45 bombers would now lose only 12. That was 33 fewer B-17s lost per mission. A B-17 bomber cost $238,000. 33 B-17s represented $7,854,000. More importantly, it represented 330 aircrew not killed or captured. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The 8th Air Force flew approximately 2 major bombing missions per week in early 1944. Over a year, extended-range escort capability would save approximately 3,432 bombers and 34,320 aircrew, at a cost of $720,000 in improved bearings. The return on investment was approximately 4,700 to 1. The procurement office approved full-scale bearing production in February 1944. SKF received a contract for 30,000 bearings, with delivery scheduled to begin in April. Other bearing manufacturers, including Timken and New Departure, were brought into the program to increase production capacity. Each manufacturer had to develop their own processes for achieving the required tolerances, working from the specifications Youngren provided. At 7 hours and 30 minutes, Harold Youngren authorized shutdown of the test engine at Wright Field. The bearing had survived 30 minutes longer than the longest projected Berlin Escort mission. The engineers gathered around as the engine wound down, the propeller gradually slowing until it stopped. The gearbox temperature began dropping immediately once the engine shut off and oil circulation ceased. They waited 20 minutes for the engine to cool enough to safely disassemble the reduction gearbox. Youngren's hands were steady as he removed the gearbox cover bolts, but several other engineers later recalled that he appeared more nervous during this disassembly than during the entire 7.5-hour test. The bearing's survival during operation proved it could handle the thermal and mechanical loads. But the real test was whether it showed any signs of impending failure, anywhere patterns or discoloration that would indicate it was approaching its limits. The gearbox cover came off, revealing the gear train and bearing assemblies inside. Everything was coated with oil, which was normal. Youngren carefully removed the output shaft assembly, which held the critical bearing. He wiped the bearing surfaces clean with lint-free cloth and examined them under bright light, looking for any signs of wear, scoring, or discoloration. The bearing looked nearly new. The raceway showed the normal polishing that occurred during operation, but no scratches, no pitting, no scoring. The balls were similarly unmarked. Youngren took the bearing to the inspection room and measured the clearances with precision instruments. The radial clearance measured 1.65 thousandths of an inch. It had increased by 0.15 thousandths during the 7.5-hour test, an increase so small it was barely above the measurement uncertainty of the instruments. This was the evidence Youngren needed. A bearing approaching failure would show clearance increase of several thousandths as wear accelerated. This bearing showed essentially no wear. More importantly, the wear pattern was uniform, indicating that the oil film had been maintained consistently across all contact points throughout the test. The reduced clearance design was working exactly as predicted. Youngren wrote his report that afternoon. He concluded that bearings manufactured to the new specifications could reliably support 8-hour missions with substantial safety margin. He recommended immediate installation in all P-51D aircraft beginning production, and retrofit kits for P-51B and C models already in service. He estimated that aircraft could begin arriving in England with the improved bearings within 60 days if procurement and production proceeded without delay. The Army Air Forces accepted Youngren's recommendations on March 8, 1944. North American Aviation received authorization to begin installing the new bearings in P-51D aircraft on the production line. Packard Motor Car Company began assembling retrofit kits for engines already delivered to England. By early May, the first P-51 Mustangs equipped with Youngren's bearings arrived at 8th Air Force bases in England. The combat test came on March 6, 1944, though the aircraft involved didn't have Youngren's improved bearings yet. The 8th Air Force launched the first American fighter escort mission to Berlin. 62 P-51 Mustangs from the 4th Fighter Group took off from Debden, England, at 0800 hours. They carried full internal fuel plus two 75-gallon drop tanks each. The round-trip distance was 1,140 miles. Expected flight time was 7 hours and 20 minutes. The mission profile was carefully planned to maximize range. The fighters would climb to 25,000 feet while still over England, allowing them to reach altitude while fuel was most plentiful. They would cruise at indicated airspeed of 260 miles per hour, the speed that provided optimal fuel efficiency for the Merlin engine. They would drop their external tanks when empty or when combat required maneuvering that made the tanks a liability. Captain Don Gentile, leading one flight of 4 aircraft, later described his concern about the mission duration in his combat diary. He wrote, 7 hours is a very long time to sit in a fighter cockpit. But the real worry was whether the engines would hold together. We'd heard about bearing problems on extended missions. Nobody wanted to be halfway to Berlin and have an engine seize up. The fighters rendezvoused with the bomber formation over the North Sea and escorted them across the German border. Luftwaffe fighters rose to intercept but were engaged by the P-51s before they could attack the bombers. The aerial combat was intense but brief. The German pilots seemed surprised to encounter American fighters this far into Germany. Several broke off their attacks and retreated when they realized the P-51s were present. The bombers reached Berlin and dropped their bombs on industrial targets through heavy flak. The P-51s maintained position, unable to help against the anti-aircraft fire but providing protection against fighter attack. After the bombing run, the entire formation turned west and began the long flight back to England. 3 P-51s from the 4th Fighter Group experienced mechanical problems on the return flight. One had an oil leak that forced the pilot to reduce power to prevent engine seizure. He made it back to England but landed at an emergency airfield closer than his home base. Another had a coolant leak that caused engine temperature to rise dangerously high. The pilot nursed the aircraft home, landing with the engine temperature gauge well into the red zone. The third aircraft, flown by Lieutenant Richard Peterson, experienced a bearing failure in the accessory drive section of his engine at approximately 6 hours and 45 minutes into the mission. He was over Belgium, still 90 miles from the English coast. The bearing failure caused his generator to stop functioning, depriving the aircraft of electrical power. His radio went dead. His gyroscopic instruments began winding down. Most critically, his fuel gauges stopped working, leaving him with no way to know how much fuel remained. Peterson had a choice. He could bail out over Belgium and become a prisoner of war, or he could attempt to reach England flying without instruments and without knowing his fuel status. He continued flying west, using the sun's position and his knowledge of geography to navigate. He crossed the Belgian coast and the English Channel, and spotted the white cliffs of Dover. His fuel situation was desperate by this point, but he had no way to know exactly how desperate. He spotted an RAF fighter base and entered the landing pattern without radio communication, hoping the tower controllers would recognize his situation and clear him to land. They did. Peterson landed safely with his engine still running. Ground crew estimated he had perhaps 5 minutes of fuel remaining when he touched down. The other 59 P-51s from the mission returned to their bases in England. 55 landed at their home fields. 4 diverted to closer airfields due to fuel concerns or mechanical issues. All pilots reported engine performance that was generally satisfactory, though several noted unusual noises or vibrations late in the mission that suggested components were operating near their limits. The mission debrief at 4th Fighter Group headquarters on the evening of March 6 lasted until after midnight. Pilots reported their experiences, maintenance officers examined the aircraft, and intelligence officers compiled combat reports. The mission was declared a success. American fighters had escorted bombers to Berlin and back, proving it could be done. But the mechanical concerns were significant enough that the 8th Air Force temporarily limited further Berlin missions until engine reliability could be improved. This was exactly the situation Harold Youngren had anticipated. The P-51 had sufficient fuel capacity to reach Berlin, but the engines couldn't reliably survive the extended operation required. His bearing redesign would solve this problem, but the improved bearings wouldn't reach operational units for another 60 days. The 8th Air Force would have to choose between launching Berlin missions with existing aircraft that had marginal reliability, or waiting for improved aircraft and giving the Germans 2 more months to strengthen their defenses. General James Doolittle, commanding the 8th Air Force, chose a middle path. He authorized continued Berlin missions but limited their frequency to once per week, allowing maintenance crews more time to inspect and service engines between missions. He also ordered that any aircraft showing signs of excessive engine wear be grounded until improved bearings were available. The second Berlin mission launched on March 8, 1944. This time, 83 P-51s participated, flying from multiple fighter groups. The mission profile was similar to the first, with the same concerns about engine reliability. 2 aircraft aborted due to mechanical problems before reaching Germany. The remaining 81 completed the mission without major incident, though several pilots reported engine issues that required attention after landing. Post-flight inspections revealed bearing wear patterns that concerned maintenance officers. 3 engines showed metal particles in their oil filters, indicating bearing degradation. 2 engines had bearings that showed early signs of scoring on the raceways. These engines were removed from service pending availability of replacement parts. The bearing problem was clear and measurable. Every extended-range mission to Berlin was causing cumulative damage to engine bearings that would eventually result in failures. The mathematics were troubling. If each Berlin mission degraded bearings to the point where 3% of aircraft required engine changes afterward, and the 8th Air Force needed to maintain a force of at least 200 combat-ready P-51s for escort duties, then every 10 Berlin missions would require 60 engine changes. The engine depot at Brettonwood, England, could process approximately 20 engine changes per week. This meant the operational tempo was limited by bearing life, not by pilot availability or aircraft production. Component failure analysis at Brettonwood confirmed what Youngren had predicted. The standard bearings with 0.005 clearance were experiencing oil film breakdown at temperatures above 210 degrees Fahrenheit. Once oil film breakdown occurred, even briefly, were accelerated exponentially. A bearing that showed early wear on one mission would fail on the next. The only solution was to replace bearings preemptively, before they reached the critical wear point. This created an enormous logistics burden. Each Packard Merlin engine contained approximately 40 bearings of various sizes. 12 of these were critical high-stress bearings in the reduction gearbox and accessory drives. Replacing all 12 bearings in an engine required approximately 16 hours of labor by skilled mechanics, working in often miserable conditions in unheated hangars in England during winter. The 8th Air Force maintenance system in England employed approximately 18,000 personnel supporting bomber and fighter operations. Of these, roughly 3,000 were engaged in engine maintenance and repair. These mechanics and technicians worked around the clock, 7 days per week, keeping engines operational. They dealt with combat damage, mechanical wear, and the environmental challenges of operating high-performance engines in damp, cold conditions. Adding bearing replacement to their workload strained the system. Mechanics who had previously inspected engines and returned them to service now had to disassemble reduction gearboxes, measure bearing clearances, replace any bearing showing wear, reassemble the gearbox, and test-run the engine. The inspection and replacement process took time away from other critical maintenance tasks. Supply logistics were equally challenging. Bearings manufactured to Youngren's specifications wouldn't arrive until May. In the meantime, the 8th Air Force had to maintain operations with existing bearing stocks. Standard bearings were in plentiful supply, but they couldn't survive Berlin missions reliably. The supply officers had to balance immediate operational needs against long-term engine health. Colonel Kashoff, who oversaw 8th Air Force maintenance operations, later wrote in his after-action report, "The bearing situation created a critical bottleneck in fighter operations during March and April 1944. We had sufficient aircraft, sufficient pilots, and sufficient fuel to escort bombers throughout Germany. But we couldn't maintain operational readiness because engine bearings were wearing out faster than we could replace them." The solution was to reduce mission tempo, which was unacceptable from a strategic standpoint, or to accept higher mechanical failure rates, which was unacceptable from a safety and loss standpoint. The solution arrived in early May when the first shipment of Youngren's improved bearings reached England. The bearings came packed in sealed containers with detailed installation instructions. Each bearing was individually marked with a serial number and inspection data. Mechanics were instructed to measure bearing clearances during installation to verify specifications, using precision micrometers provided with the bearing shipment. Installation began immediately on P-51 aircraft dedicated to long-range escort duties. Maintenance crews worked through the night to retrofit engines with the new bearings. By mid-May, approximately 120 P-51 aircraft were equipped with improved bearings. These aircraft were reserved for Berlin missions and other deep penetration escort duties. The operational test came on May 8, 1944, when the 8th Air Force launched a maximum effort against oil refineries and marshalling yards in Germany. Over 800 bombers participated, escorted by more than 400 fighters including 135 P-51s equipped with Youngren's bearings. The mission duration exceeded 8 hours for several fighter groups that had to divert around weather systems. All 135 P-51s with improved bearings completed the mission and returned safely to their bases in England. Post-flight inspections revealed no unusual bearing wear. Oil analysis showed no metal particles. Engine performance was normal. The bearing redesign had worked exactly as Youngren predicted. P-51 Mustangs could now reliably escort bombers anywhere in Germany and return home. By June 1944, the transformation was measurable in ways that combat commanders could quantify with precision. The 8th Air Force flew 23 major bombing missions into Germany during June. Fighter escorts accompanied every mission, regardless of target location. Berlin, Munich, Vienna, targets that had been beyond reliable escort range in March, were now covered by P-51 Mustangs flying 7 to 8 hour missions without mechanical failures. The bomber loss rates told the story with stark clarity. In October 1943, during the disastrous Schweinfurt raid, the 8th Air Force lost 20% of attacking bombers. In February 1944, before improved P-51 coverage became widespread, average bomber losses per mission ran at 12 to 15%. By June 1944, with P-51s equipped with Youngren's bearings providing comprehensive escort, bomber losses averaged 3.7% per mission. This wasn't just statistical improvement. It represented human lives. In practical terms, a typical mission of 600 bombers that would have lost 90 aircraft and 900 crew members in October 1943 now lost 22 aircraft and 220 crew members. 68 fewer bombers destroyed. 680 fewer men killed or captured. Every mission, every week, throughout the summer of 1944. The Luftwaffe recognized what was happening and understood the implications. German fighter commanders had built their defensive strategy around the assumption that American fighters had limited range. They positioned their interceptor groups inland, beyond escort range, where they could attack bomber formations with relative impunity. This strategy collapsed when P-51s began appearing over targets throughout Germany. German tactical intelligence reports from June 1944, captured after the war, expressed confusion about American fighter capabilities. One report stated, enemy escort fighters now appear over all target areas regardless of depth of penetration into Reich territory. Previous calculations of American fighter radius of action have proven incorrect. Defensive tactics must be revised. The Luftwaffe attempted to adapt by engaging American fighters directly rather than avoiding them to attack bombers. This played into American advantages. The P-51 was faster, more maneuverable, and more fuel-efficient than most German fighters. In fighter versus fighter combat, the P-51 groups consistently achieved favorable kill ratios. Throughout June and July 1944, American fighter groups destroyed German aircraft at rates approaching 3 to 1. The mathematical reality was brutal for the Luftwaffe. They were losing fighters faster than their training system could replace pilots. They were losing experienced fighter leaders who couldn't be replaced at all. By August 1944, the Luftwaffe's day fighter force was approaching collapse, not primarily because of aircraft shortages, but because of pilot losses. Meanwhile, maintenance records from 8th Air Force bases in England documented the reliability improvement that Youngren's bearings enabled. In March 1944, before the improved bearings arrived, approximately 18% of P-51 missions resulted in some form of mechanical abort or post-flight engine issues requiring component replacement. By July, with improved bearings installed fleet-wide, mechanical abort rates had dropped to 4.2%. The bearing changes weren't the only factor in this improvement. Maintenance procedures improved, mechanics gained experience with the Merlin engine, and supply chains matured. But the bearing redesign eliminated the single most common cause of engine failures on extended missions. Engines that previously required major inspection every 40 flight hours now ran reliably for 80 to 100 hours between inspections. Colonel Kasshoff's maintenance reports from July 1944 noted, the bearing modification has proven its value beyond question. We can now plan deep penetration missions with confidence that mechanical reliability will not compromise operational effectiveness. The strategic bombing campaign that Harold Youngren's bearing made possible reached its culmination in what later analysts called Big Week, though the decisive phase actually extended from February through August 1944. The mathematics of attrition worked relentlessly in favor of the Americans once P-51s could escort bombers throughout Germany. The Luftwaffe lost approximately 1,000 fighter pilots killed in action between March and August 1944. Their training system graduated approximately 600 new fighter pilots during the same period. The deficit was unsustainable. By September 1944, the average experience level of Luftwaffe day fighter pilots had dropped from over 400 combat hours to less than 100. Veteran leaders who understood advanced tactics were gone, replaced by inexperienced pilots flying outdated defensive strategies. This collapse enabled the destruction of Germany's oil production capacity, which was the actual strategic objective of the bombing campaign. Bombers escorted by P-51s destroyed synthetic oil plants at Lohme, Blechhammer, Politz, and Bruchs. German fuel production dropped from 175,000 tons per month in March 1944 to 20,000 tons per month by September. This fuel shortage grounded much of the remaining Luftwaffe and immobilized Wehrmacht armored divisions during the critical battles in France and on the Eastern Front. Harold Youngren received no public recognition for his bearing redesign. The Army Air Forces classified the technical specifications as militarily sensitive information. Bearing manufacturers were forbidden from discussing the improved tolerances or manufacturing processes. Youngren's name appeared in internal Army reports and procurement documents but nowhere else. After the war ended, Youngren returned to Packard Motor Car Company's civilian division. He worked on automotive engine development until Packard ceased automobile production in 1958. He then joined the Bendix Corporation, working on aircraft components until his retirement in 1967. He died in 1972 at age 67 in Ann Arbor, Michigan. No obituary mention his contribution to the P-51 program. His family learned the full story only years later when an aerospace historian researching Wright Field test records discovered Youngren's reports and contacted his daughter. She had known her father worked on aircraft engines during the war but had no idea his work had been critical to strategic bombing operations. The bearing technology Youngren developed had a legacy that extended beyond World War II. The manufacturing processes SKF and other companies developed to achieve 1.5 thousandths of an inch tolerances became standard practice for precision bearings in jet engines, turbines, and other high-performance applications. Modern aircraft engines contain hundreds of precision bearings manufactured using descendants of the processes developed to meet Youngren's specifications. The U.S. Air Force Historical Division published a comprehensive study of fighter escort operations in Europe in 1949. The study concluded, the extension of escort fighter range to cover all target areas in Germany was the decisive factor enabling the strategic bombing campaign to achieve its objectives. This extension depended on engine reliability improvements that allowed fighters to operate for extended durations without mechanical failure. The study identified bearing improvements as one of several critical modifications, alongside fuel tank additions, engine refinements, and tactical innovations. It did not mention Youngren by name. The technical specifications remained classified until 1978, when the Air Force declassified World War II procurement documents. By the time the documents were declassified, Youngren was dead. The historical record credited the P-51's success to North American aviation's designers, to the Rolls-Royce Merlin engine, to the pilots who flew the aircraft. The bearing that made 8-hour missions possible was a footnote, the engineer who redesigned it was forgotten. That morning in March 1944, when Harold Youngren stood in the observation room at Wright Field watching a bearing spin for 7.5 hours, he was testing more than a mechanical component. He was testing whether American industrial precision could solve a problem that seemed unsolvable. Whether manufacturing tolerances measured in 10,000ths of an inch could translate into strategic advantage. Whether the discipline required to grind steel to within millionths of an inch of perfect smoothness could matter as much as courage in combat. The answer was yes. It mattered enormously. The bearing that shouldn't have survived enabled missions that shouldn't have been possible, which destroyed a defensive system that shouldn't have been defeatable. The connection between these outcomes wasn't obvious. No single bearing defeated the Luftwaffe. But without bearings that could survive 8-hour missions, P-51s couldn't escort bombers to Berlin. Without escort to Berlin, the bombing campaign couldn't destroy oil production. Without oil, the Luftwaffe couldn't fly and the Wehrmacht couldn't maneuver. This is how wars are actually won. Not through decisive battles where armies clash and one side prevails through superior valor, but through accumulation of small advantages that compound into overwhelming superiority. A bearing that lasts 8 hours instead of 4. An oil film 50 millionths of an inch thick that doesn't break down at high temperature. Manufacturing processes that achieve rejection rates of 28% but deliver components that actually work when everything else fails. The cost of getting this right was measurable. $720,000 for improved bearings. Countless hours of engineering work. Months of manufacturing development. Arguments with procurement officers and bearing manufacturers who said it couldn't be done. The cost of getting it wrong was also measurable. 200 American bombers lost per month. 2,000 aircrew killed or captured. Strategic objectives unachieved, prolonging the war. Youngren spent 8 months of his life working on a single problem that most people would consider trivial. He redesigned a component that weighed less than 2 pounds and measured 3.5 inches in diameter. He argued about manufacturing tolerances and measurement procedures. He ran tests and wrote reports and fought with bureaucrats who couldn't see why any of this mattered. And then 68,000 American aircrew flew missions over Germany escorted by fighters that could reach anywhere because their engines didn't fail. Most of them never knew why their engines worked reliably. Most of them survived the war and went home and lived their lives without ever knowing that a bearing existed that made their survival possible. This is the truth that the 8th Air Force discovered between March and August 1944. Strategic bombing required more than bombers and bombs. It required the entire industrial system working at levels of precision that seemed impossible. It required engineers willing to violate standard design principles when standard design principles weren't good enough. It required manufacturers willing to accept rejection rates that destroyed profitability because the components that passed inspection were genuinely superior. It required someone like Harold Youngren, standing in a test facility on a cold morning in Ohio, watching gauges and listening to an engine that had been running for 7.5 hours, waiting to see if his calculations were correct. If the physics he believed in would actually work. If 50 millionths of an inch of oil film would save lives he would never meet. The bearing survived. The mission succeeded. The war was won by engineers and mechanics and factory workers whose names appear nowhere in the histories but whose precision made everything else possible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.